Okay, welcome everybody. We're going to look at the next section, section 7.6, making comparisons. So a couple more tests in this chapter. The first one is what they're calling theorem 7.m, and it's called the direct comparison test. Okay, so whenever you're citing a test, you'll say 7m, you'll say direct comparison test. Here's how it goes. We have a sequence as part of a series, 1 to infinity of a sub n and 1 to infinity of b sub n. They're both positive series, and suppose that b is greater than a for all n greater than n. So that means that after a certain point, b dominates a. Then if b converges, so does a. It's a pretty simple concept, right? If after a certain point, so it could be that for the first, couple million terms even, a could be bigger than b. But after a certain part, if you go far enough out in the series, then eventually b gets bigger than a. So the sequence gets bigger eventually after a certain amount of time. If that ends up happening at the end of the day, and if b converges, then a converges. So that makes a lot of sense, right? If b is bigger than a and b goes somewhere, then a has to go there too. Okay, that's the idea. Let's look at a corollary to that. So the corollary to that is the power series, okay, here. This is not a power series exactly, right? But it's similar to a power series. So anytime I have a series that looks like this, I'm going from 1, or any finite number, to infinity, and it's 1 over into some positive p. So again, p has got to be bigger than 1, strictly bigger than 1. And we're adding a positive number down here, so 1 to any positive number here. This converges. Well, we can use the direct comparison test. We know that if c is bigger than 1, then this has got to be less than 1 over n to the p. But we know that this series is convergent as long as p is bigger than 1, because this is a p series. So since this series converges for p bigger than 1, and since n 1 over n to the p is always bigger than 1 over n to the p plus c, that means that this converges too. Okay? So this sequence converges, this series converges for c positive and and p greater than 1. Let's look at some other examples. So the first one here. So we have a sense that this should converge because of the it looks like a p series, okay? And indeed that's basically what it is. So remember that n is from 0 to infinity, so n is always a positive number. So what we're going to do is we're going to compare this sequence with this sequence. How do they compare? Well, n squared is a positive number, so if I compare n squared to itself, that's fine. But this term, these terms here, are always bigger than 0, okay, for n after a certain point, n bigger than 1. So this is always, it's always bigger than 0. So these numbers are always bigger than 0. That means that 1 over that, this denominator will always be bigger than this denominator, which makes the entire fraction smaller, because that's the reasoning. So this, however, from n equals 0 to infinity, converges, since this is a p series with p bigger than 1. So since this converges and this sequence dominates this sequence, we have a convergent series. Let's try the second one here. Remember, this is only to show convergence. It doesn't say anything about divergence yet. Okay. All right, so let's see here. We've got this situation. We have to figure out a way to build this now. All right, well, let's start off with something like this. Let's compare this with this. This is 5 over 2. Okay. Well, we compare these two now. Again, as long as n is bigger than 1, this is bigger than 0. This is a positive number, which means that no matter what, that dominates. Okay. But we haven't quite got it yet. Now we have the numerator. The numerator here is n. So what I have to do is multiply both numerators by n. And I can do that without flipping the inequality since n is positive, because it's an index, it's a whole number. So this is what I have. N over square root of n to the fifth plus n cubed minus 1 is less than or equal to this, which is n to the first divided by n to the 5 halves. Okay, so I can write this as let's see, 1 over 5 halves minus 1 is going to be n to the 3 halves. Okay, now this sequence will converge since 3 halves is bigger than 1. So since this converges and this sequence dominates this sequence, our original function, our original sequence converges, our original series converges. Okay, so let's take a look at 1 over ln of n. What happens is n is bigger than 2. Now we let n be 2 or greater because ln of 1 is 0 and that would cause a problem. Now, we'd like to be able to compare this with something we know, like a p-series. A p-series is a great thing to compare it to. So maybe if we try something like 1 over ln of n compared with 1 over n. Okay, well, so this is kind of an interesting point here. We'd like to compare these two. So let's take a look and see what the comparison is. Again, we're always trying to compare something we know, and this is probably the closest thing I'm going to find to something I know. All right, so let's take a look here. If n versus ln of n. Now, in general, n is bigger than ln of n, right? ln of 1 is 0. ln of 2, let's practice this here. I don't know if this can do ln. Okay, 0.669, okay. ln of 3, 1.09, okay. So notice that in general, n dominates ln of n, which means that ln of n dominates 1 over n. Okay, so this is not exactly the way we've been using it before, but let's take a look and see what happens to 1 over n. Now, 1 over n is a harmonic series, and from n equals 2 to infinity, because that's where we're starting, this diverges. Okay, but wait a minute here. ln of n dominates 1 over n, and 1 over n diverges, which, using the contrapositive of the comparison test, means that a 1 over ln of n from 2 to infinity is also going to diverge. So basically the idea is that if the function on the bottom, or if the series on the bottom diverges, then the one on top must diverge, and vice versa. If the one on top converges, the one on the bottom must also converge. Okay, the next one is kind of a similar idea, only we're going to use limits this time. This is called the limit comparison test. And here's how it works. You take two sequences, two series, hopefully one series you know something about, okay? And you take the ratio of the two and take the limit as long as n goes to infinity. If the limit ends up being, there are three cases. If the limit ends up being finite, so it goes to a number besides 0, so a positive number that is not 0, then either both a and b converge, the sums rather, or a and b diverge, so they do the same thing. If L goes to infinity, so if the limit goes to infinity, and the numerator converges, then so does the denominator. And if L goes to 0, so if it's going to 0, then if the numerator diverges, then so does the denominator. Okay? So either they go to the same, they go to a finite number and they both converge or they both diverge. Okay, so they're going at the same rate. They go to infinity. If they go to infinity, then if the numerator converges, the denominator also does. And if they go to 0, if the numerator diverges, then the denominator also does. Okay, we're going to look at an example here in just a moment. Okay, so let's quickly kind of come up with a reasoning why that might be the case. If these go to a finite number, then that means they're going essentially at the same rate after a certain point, which means they're going to be going to 0. These sequences will be going to 0 at the same rate. Okay, so that means that if a sub n ends up summing to a finite number, then b sub n is also going to sum to a finite number, okay? And vice versa. So if you know the convergence or divergence of one, you know the convergence or divergence of the other. If we're going to infinity, okay, and we know that the numerator converges, what does that mean? That means the numerator is outpacing the denominator if it's going to infinity. So if the numerator we know converges, but it outpaces the growth of the denominator, that means the denominator is also converging because it's going slower. Okay, and if it's going slower, it's going to converge more quickly than the numerator. If they go to 0, what that means is the denominator is the denominator is outpacing the numerator. So if the denominator is outpacing the numerator and the numerator is diverging, you know automatically, since the denominator is going faster, that the denominator is also diverging. That's where it comes from. Okay, so is the infinite series convergent or divergent? All right, so we have 1 over 3 to the n minus 1. Okay, so we're going to use the limit comparison test here, and what we're going to do is we want to compare this, hopefully, with something that we know something about. And a pretty easy one to compare is 1 over 3 to the n. We know this is a geometric series when I sum it up, and we know that's convergent because it's 1/3 to the nth power, and 1/3 is less than 1. Okay, so let's compare these two. So we're going to compare them as a ratio and see where this goes. Okay, so we invert and multiply with the limit as n goes to infinity of 3 to the n over 3 to the n minus 1. What that lets us do is notice again that the constant term doesn't do anything, so this is going to go to 1. Okay. What does that mean? That means that since the numerator we know, since the denominator we know is convergent, and we know this goes to a finite number, then that means the numerator is also convergent. Okay, this infinite series here, is it convergent or divergent? Now this is a tricky one. I had to think about this a bit. Well, let's take a look at this. Now, with limits, remember, the glorious thing about limits is we can kind of ignore lesser terms typically. So what do we have here? We have a 3, that's not going to matter much. We have an n, an ln n, we have an n squared, and we have a 7. That 7's not going to matter much. So effectively, we're kind of looking at this. Okay. So, without the 7 on the bottom. Okay. Well, this is just ln of n over n. Now, one of the exercises from the last homework said that by the integral test, that this is divergent. That's good to know. So we know something about something that we can compare to this. So let's see if perhaps we can compare ln of n over n to this in some way. Let's take a look at the limit as n goes to infinity of, we'll start 3 plus n ln n divided by n squared plus 7, all divided by ln of n over n. Okay. And again, we know this is divergent. Okay, so we'll do 3 plus n ln n divided by n squared plus 7 times n over ln n. Okay, so let's see what we can do. Distribute the n through, we get limit as n goes to infinity of 3n plus n squared ln n divided by n squared ln n plus 7 ln n. Okay, so we're getting somewhere now. What I'm going to do now is multiply the numerator and denominator again by 1 over the largest term to see if I can figure out how to deal with this. What am I left with? I'm left with 3 over n plus ln of n divided by, that should be the limit of this, pardon me, ln of n plus 7 ln of n over n squared. Aha, this we can figure out. This will go to 0. This will go bigger. This will go bigger. This will go to 0. This entire thing, since this is going to 0 and this is going to 0, these are going at the same rates, is going to 1. So this entire limit is going to 1, which means that since we know that the denominator series diverged, so will the numerator series. So this is divergent by the limit comparison test. Pretty cool. All right, so now we've added a couple more tricks to the bag. We have the divergence test. This is the order which you should probably check these out. Divergence test. That's when we're looking to see what does the limit of the sequence do. The p-series test, that's 1 over n to the p. The geometric series test, that's where we raise something to the n. Direct comparison test, that's where I compare one we just learned. We see which series dominates which one. The integral test, okay? This is the one where we turn it into an integral and see if we can integrate that and see if it converges. The limit comparison test we just did, telescoping series and partial sums are from a previous section. Now, the reason these go from easiest to hardest. The direct comparison test was pretty easy, right? First of all, we can recognize a p-series, no problem. We can see if something goes to infinity, J0, no problem. We can recognize a p-series, no problem. We can recognize a geometric series, no problem, because it's just raised to the n power. The direct comparison test, all this is, can we find a function or a sequence that we know about that's bigger than or smaller than? That's the direct comparison. The integral test requires integrating, which isn't always fun, but sometimes it can work. The limit comparison test is harder because we have to find, you saw that, right? We had to find a limit that we could take a ratio of that we knew something about that was going to make the limit easier to compute. And the telescoping series and partial sums are quite a bear sometimes. Okay, that's it though. All right, we're going to look at this in class next time.